Hi, my name is Shiri. I'm a PhD. And today I'll talk about joint work with Moshe Babaioff and Shahar Dobzinski, which is about the computational complexity of mechanism design in single crossing settings. So in mechanism design, we have a set of outcomes O and strategic players, and each player I has a private valuation function called the evaluation function that specifies its value for every outcome. The valuation function Vi is private and belongs to a set of valuations that is known in advance, which we call the domain and denote with capital Vi. Now we want to map every valuation profile to an outcome and to a payment for each bidder. And when doing so, there are usually two aspects that you want to take into account. First, you want to maximize or approximate some objective function. And a classic objective function is welfare maximization, which is maximized when we output the outcome that maximizes the sum of the values of the players. The second aspect that we care about is the strategic aspect. Since the players are strategic and their values are private, we need to take that into account. And what we mean by that is we want to design the function and the payments in a way that guarantees that no player I ever increases his profit, which is his value for the outcome minus the payment, by misreporting his valuation. And as computer scientists, we do not only care about the objective function and the incentives, but we also care about the running time. And throughout the talk, we do not talk about other incentive compatibility notions besides dominant strategy incentive compatibility. So I'll just say incentive compatible or truthful instead of dominant strategy incentive compatible. In addition, we focus on deterministic mechanisms. So the basic question in algorithmic mechanism design is whether polynomial time algorithms are as good as polynomial time truthful mechanisms. And this question repeats itself for various objective functions and settings. And actually, for several problems, we know that the answer to it is yes. So let's go over some of these problems. One such problem is scheduling jobs to machines, where our goal is to minimize the completion time of the last job, which is called the makespan. And each job we care about the setting where each job has some size, and each machine has some speed, which is its private information. And each machine wants to get the highest possible payment and do as little work as possible. Now, if we neglect strategic considerations, then there is a classic polynomial time approximation scheme. And there is also a truthful polynomial time approximation scheme. Another such setting where truthfulness is not a barrier is the setting of single-minded bidders in a combinatorial auction. So a combinatorial auction with single-minded bidders is an auction where the items are different from each other, and each bidder is interested in only one specific subset of items. And our goal is to output an allocation of the items to the bidders that maximizes the social welfare. And for this problem as well, it was shown that both polytime algorithms and truthful mechanisms have the same approximation power. Similarly, if we consider welfare maximization for single-minded bidders in an auction with identical items called multi-unit auction, then again, truthful polynomial time mechanisms are as powerful as truthful polynomial time algorithms. Sorry, truthful polynomial time mechanisms are as powerful as polytime algorithms. And note that these problems all share one thing in common. They are all considered single parameter, which means that the private information of each strategic agent is one-dimensional. However, if we look at the same problems where this private information is multidimensional, then we see a completely different picture. For example, if we want to minimize the completion time, where each machine has different speed for different jobs, then there is a polytime algorithm that gives a true approximation to the welfare, while no truthful mechanism gives approximation better than n, the number of machines. Similarly, for welfare maximization with multidimensional valuations, polytime algorithms achieve approximation better than 2, whereas the best polytime truthful mechanism get only a polylogarithmic approximation to the welfare. For multi-unit auction, we also have non-truthful fully polynomial time approximation scheme, but the best truthful mechanism gives us only a 2 approximation. So by that, we can conclude that mechanism design in single parameter domains has been pretty successful compared to multi-parameter domains. And this raises the question of whether truthfulness can be a barrier for single parameter mechanism design, because all we've seen are problems where it is not a barrier. And more formally, what we are asking is whether there even exists a problem where polytime algorithms are more powerful than polytime truthful mechanisms. And another question that we might be tempted to ask, given these findings, is what makes mechanism design in single parameter domains so successful? And a common explanation for that is that single parameter domains satisfy the well-known characterization that says that a function has a truthful mechanism if and only if it is monotone. But in fact, we show that there is a richer class of valuations that satisfy this characterization. And this class was introduced by Spence and Mirrlees in the 70s. And this is the class of valuations that economists have often referred to as single parameter or one-dimensional in their work. And in the next slides, we will define this class. But before that, note that if we think of single crossing as the right definition for single parameter, then the question that we should be asking is whether for single crossing domains, there is a problem such that polytime algorithms are more powerful than polytime truthful mechanisms. And we answer this question in the affirmative by providing an objective function that has a polytime algorithm that gives a constant approximation factor to the objective function, whereas every polynomial time truthful mechanism can only give unbounded approximation ratio, given a standard computational complexity assumption. However, it is important to say that the objective function for which we show this separation is quite artificial. Therefore, we also wanted to examine a natural objective function. So we looked at single crossing bidders in a multi-unit auction and discovered that for this natural problem, we have that polytime algorithms are as powerful as polytime truthful mechanisms. And along the way, we show a different, and what we discovered when devising this truthful fully polynomial time approximation scheme is another FP test for the problem of single-minded bidders that relies on a different and more direct technique that we have developed and that I'll be happy to talk about offline. Okay. So the definition of single crossing domains is not only for auctions, but all the results in the paper are in the context of multi-unit auctions. So I'll start by describing this setting. So in a multi-unit auction, we have n bidders and m identical items. And every bidder I has a valuation function, vi, which is its private information and specifies its value for every quantity of items. And a natural objective function is welfare maximization, which is, as I said, means that we want to allocate the items among the bidders in a way that maximizes the sum of the values of the bidders. So now let's finally explain what is single crossing. So for ease of presentation, we will only explain it in the setting of multi-unit auctions, but the real definition is much more general than that. So basically, a single crossing domain of valuations of some bidder, say bidder I, is an ordered domain such that for every two valuations, B2 and B1, such that the index of B2 is higher than the index of B1. And for every two quantities, S2 and S1, where S2 is larger than S1, we have that the margin of V2 between S2 and S1 is larger than that margin of valuation of V1. For example, observe the following set of three valuations, V1, V2, and V3. And we use the following graph to describe them. Each line in the graph represents one valuation, and the x-axis represents a quantity of items, and the y-axis represents the value for this quantity. For example, valuation B1 has value 0 for 0 items, value 1 for 1 item, and value 1 also for 2 items. And in the graph, you can see that the domain is single crossing because the differences between 1 item and 0 item increase with the index of the valuation, and the same holds for the difference between 2 items and 1 item. Now let's see a counterexample. Note that this domain is not single crossing because the difference between 2 items and 1 item is 1 for V2, but it is 0 for V3. So why should we even care about this class of valuations? So first of all, I believe that its economic motivation is fairly natural. We just assume that valuations are ordered and that a higher valuation signifies willingness to pay more for an increase in quality. And second of all, it's single parameter where the index of each valuation is its parameter, and it satisfies the characterization of monotone if and only if truthful, up to a small tie-breaking condition that I will not get into. And in fact, this is the largest class of valuations where all monotone functions have truthful mechanisms. And in particular, it contains all the problems that were previously considered as single parameter, such as scheduling related machines, single-minded bidders in a combinatorial auctions, and single-minded bidders in a multi-unit auction. Therefore, we believe that we shouldn't be asking whether mechanism design can be challenging for single parameter domains, but rather ask whether there is a problem in a single crossing domain where polytime algorithms are more powerful than polytime truthful mechanisms. And as I said before, we answered this question in the affirmative. And to illustrate the theorem, we will use the diagram of the desired properties of algorithms that I've shown you before, where I remind that these properties are polynomial running time, approximation to some objective functions, and incentive compatibility. So what we claim is that there exists an objective function. Well, formally, an objective function is some function that takes as an input the valuation profile of the bidders and some outcome and gives us a score. So we have such an objective function that satisfies that there is a polytime algorithm that gives a two approximation to it. But every incentive compatible mechanism that gives a finite approximation to it is TF&P hard, where TF&P is the class of total search problems. So by saying that a problem is TF&P hard, we mean that it is at least as hard as computing a Nash equilibrium, which is conjectured to be NP hard. And in addition, the hardness is because of requiring both polynomial running time and incentive compatibility, as there exists an incentive compatible mechanism that optimizes this objective function, but it requires exponential running time. However, one drawback of this construction is that the objective function for which we show this separation is not natural. So again, it raises the question of is there a natural objective function for which you have this separation? And a quite natural objective function to think of is welfare maximization. So we started investigating the approximation power of truthful mechanisms with single crossing feeders in a multi-unit auction, where the objective function is welfare maximization. And we showed that for this problem, truthful polytime mechanisms are as powerful as polytime algorithms. And we do that by showing that there is a fully polynomial time approximation scheme for that problem. And this result is our main technical contribution. While on the other hand, we show that exact welfare maximization is NP-hard, and this is true regardless of strategic considerations. And therefore, a fully polynomial time approximation scheme is the best that one could hope for. And we managed to achieve that with the truthful mechanisms. And this is how we get that algorithms and truthful mechanisms have the same power in this setting. And when devising the truthful mechanism for single crossing bidders in a multi-unit auction, we rely on a new technique for incentive-compatible rounding, which we also use to devise another incentive-compatible F-pitas for single-minded bidders, in addition to the classic one of Grist, Krista, and Woking. So to conclude, I'll present some open questions. So the first question is one that we've already discussed, is whether there is a separation for single crossing domains when the problem is natural. We ruled out a separation in the context of welfare maximization in a multi-unit auction, but there are other problems where there might be a gap. And a candidate for the next problem to explore will be, in our opinion, will be a combinatorial auction with single crossing bidders. And another long-standing open question is understanding the approximation power of truthful mechanisms in a multi-unit auction with general valuations. We know that there is a fully polynomial time approximation scheme, which is not truthful. And the best truthful mechanism that we know of gets half of the welfare. So there is a big gap here in our understanding. And that's it. Thank you for listening. I'll be happy to chat about the paper, so feel free to reach out to me.